Welcome to the fourth video in our Geotechnical Hazard Awareness series. In the last couple of videos, we explored shear strength and its key components.
But what we haven't talked about yet is how geotechnical engineers actually measure shear strength, compared to what we are focusing on in these videos. In technical practice, shear strength is measured through two main parameters: cohesion and the angle of internal friction. Cohesion is the part of a material's strength that holds it together even without any pressure acting on it. It's the natural stickiness or bonding of the material. The angle of internal friction is how well the material resists sliding over itself when force is applied. Basically, it describes how rough or interlocked the particles are.
However, in this series, we are approaching it a little differently. Rather than jumping straight into technical measurements and modeling like a geotechnical engineer would, we're starting with what we can see and recognize in the real world. We're building an understanding based on tangible features, using our eyes and experience first. From there, we'll work towards understanding how those visible features relate to strength, stability, and hazard potential. It's a practical approach aimed at building real-world awareness and giving you the tools to better observe and assess your surroundings.
So, let's get into it. In today's video, we're going to focus on the concept of center of gravity and how it applies to assessing hazards in a mining work area. Understanding where the center of gravity lies, whether it's within a slope, a rock block, or a wall, is critical to recognizing how and why instability can develop. Following this video, we'll finally move into some real-world practical examples.
But today, we have one more technical discussion to work through, and it's an important one. By the end of this session, you'll be better prepared to interpret what you're seeing on site and to understand how a shift in load or a change in center of gravity can signal an increased hazard. When we talk about the center of gravity in rocks, we're really just talking about the point where the weight of the whole rock balances. It's like if you could hold the rock up at exactly the right spot, it would stay perfectly balanced. All of the rock's weight acts through that single point. If the center of gravity is sitting well back inside the base of the rock or slope, the rock is usually stable. But if the center of gravity moves closer to the edge or hangs out over it, the rock becomes much more likely to move or fall. The more the weight hangs outside its support, the less force it takes to cause a problem or make it unstable. Knowing where the center of gravity is helps us spot when something looks stable and when it's at risk of sliding, toppling, or failing under its own weight.
One of the easiest ways to understand how the center of gravity works is to think about your own body. When you're standing upright, your weight is balanced right through the middle of your feet. You feel steady, and the pressure is spread out evenly from your heels to your toes. But if you start leaning forward, you can feel the pressure shift toward your toes. Your center of gravity has moved forward and your body is no longer evenly supported. You're relying more on the front of your feet to keep you from falling. If you lean backward, the same thing happens, but the pressure moves onto your heels. Again, your center of gravity has shifted and you're balancing on a much smaller part of your support base. When we stand upright, our center of gravity sits roughly around our lower torso. As long as it remains positioned above the area supported by our feet, we stay balanced and stable. If we begin to lean forward without moving our feet, the center of gravity shifts closer to the edge of our base of support. If it moves too far forward, past our toes, there is no longer enough support to counteract the pull of gravity, and we fall.
So what we are really looking at is how the weight is supported based upon how the rock is positioned. Or, in other words, the same principle that applies to a human body also applies to rock slopes. Imagine a rock sitting on a slope. If the wedge center of gravity is located well inside the slope face and is supported by surrounding material, the rock remains stable. The further back from the slope surface that the center of gravity lies, the more of the rock's weight pushes down onto the supporting surfaces. This increases the clamping force and resistance along the breaks or joints in the rock, helping to hold it in place. However, as the center of gravity moves closer to the exposed face, there is less weight pressing down onto the support surfaces and less resistance against sliding or toppling. Then, especially if erosion, blasting, or excavation removes the supporting material around the anchoring point, the overall stability decreases. Now, if the center of gravity moves beyond the edge of the slope, with no material left to support it, the likelihood of instability or failure increases significantly. If the rock is toppling or leaning forward, it no longer has a resistance to sliding on the surface contacts. Therefore, it is entirely dependent on the stability of the supporting material around it. In summary, if a rock leans in a way that makes it want to slide or topple, its ability to remain stable will depend entirely on how much friction, cohesion, and support is still available to counteract gravity and other forces acting on it.
Now, with that in mind, if your weight is supported by your feet, what happens if your feet are knocked out from underneath you? You would fall. It's the same for those slabs of rock. If the material around the part of the base that is keeping it stable gets washed away, loosened, disturbed, or excavated, it's like knocking the feet out from under a person. Without anything left to hold them up, the loose rock is entirely dependent on its cohesion, friction, and ability to resist gravity. Basically, if it isn't able to stop itself from sliding, then gravity wins, and the rock or slope will fail. So even though they might look like they're leaning safely back into the hill, they're really depending on the anchoring point to stay stable and supportive. If you take that away, and the grip of the surface isn't enough to resist the force of gravity, there is nowhere to go but down.
Understanding how center of gravity, weight distribution, and ground support work together is key to recognizing why rocks and slopes either stay stable or eventually fail. Even small changes, like the removal of supporting material, can shift the balance and lead to instability.
In the next video, we'll build on what we've learned here by looking at real examples of slope and rock failures. We'll also explore some simple design strategies that can help prevent these failures from happening in the first place.
Well, we've come to the end of today's video. We hope to see you again when we post the next video in the series. Thank you for watching.